Hello, good to see you. Let's come back to see how we apply the concept we just talked about on some real problems. Okay, so here I have a compound shaft consisting of two pipe segments. Segment 1 has an outside diameter 6.5 inch and a wall thickness 0.375. Segment 2 has outside diameter 4.5 and a wall thickness 0.5. The shaft is subjected to axial compression load, okay? So you should pay attention here. I have axial compression load, all right? And a torque TB at point B and torque TC at point C here, which act on the direction shown in these figures, okay? So determine the principal stresses and maximum shear stress at point H and K on the surface of the shaft. So H and K on the surface of the shaft. Okay. B, show these stresses in an appropriate sketch for both H and K. Both H and K. Okay. So apparently I have the solution here, but let's talk about the strategy. Okay. So what we do first, so according to our last video, we make the cut first. Okay. So let's take a look on the point. So this is A. Apparently, we're looking at point H. Okay, so once we have a point H, we want to make a cut, and this is going to be my cut. Okay, the cut will be crossing H and in perpendicular to the section or to the bar. Okay, to the bar. Okay, so once I made this cut, okay, so I want to show the free body diagram, which you always have to draw. So once I made the cut, I will establish my local coordinate system, which actually has been established for me in the problem, but nevertheless, this is a local chord, and this is the point H on the side right here. Okay, so let's talk about forces that exerted on the section. Okay, so let's make a little bit table here. What type of force I have? So first of all, I have a compression of P. Okay, compression of P. Okay, and the other thing I have is I'm going to have a torsion. Okay, so this torsion here will equal to what? Will equal to TB minus TC. TB minus TC to maintain the balance, isn't it? To maintain the balance. Okay, so let me list my little table here. So my forces, right? My forces, I have an axial force now. So let's say Px, okay, equal to P, actually negative P in terms of compression. And Py equal to 0, Pz equal to 0, of course, right? So Py, Pz, all 0. Okay, so how about shear? So this is axial forces. And this is shear. How about shear? So I don't have any shear, isn't it? I have no shear in this case. Why? Because all my forces along x direction, right? All my forces is along x direction. How about moment? Do I have any moment at all? So I have mx equal to what? Equal to actually torsion, right? So you realize that torsion and the moment are actually the same thing, right? Actually, it's the same thing. They're just acting on a different axis. Okay? So this is basically TB minus TC. Okay? How about the moment in the y-axis, right? How about moment in the y-axis? I don't have any moment in the y direction. And I just want to mention that this is actually the thumb direction by the right-hand rule, okay? Right-hand rule, okay? This is basically the thumb direction. So if I want to label it, the torsion Tx is actually equal, the torsion T is actually equal to Mx is actually equal to this double arrow here, okay? Now going back, do I have any moment in the y direction? I don't. And how about Z direction? I don't. Okay, so turns out I only have two things going on. Okay, I have first the axial stresses. Okay, second, my bending moment. Okay, so take a look at H. I take a look at the point H here. Okay, and this is my cross section here. This is my neutral axis, but we don't have bending, so forget about it. Sorry, forget about the neutral axis because we don't have any bending. Okay, let me just draw my section, and this is my point H here. Okay, now let's take a look what type of stresses I have, right? What type of stresses I have. So first thing first, I will have a shear stress caused by the torsion. Okay, so tau H. Okay, and I'll have axial stress, which is actually going inside the plane, compression. Okay, so this is on the cross section. On the side view, this is my bar, this is my H, right? Zoom in here to show you in terms of a small element called H. I have compression due to P over A. Is that right? I will have also a shear stress, right? Shear stress caused by T, B minus TC over R, which is the distance between H and the center, and divided by J. Is that right? J is the polar moment inertia. Okay, so to satisfy the symmetry, this is the stress components I have on the element H. Okay, so if you follow the same process, you will find out the stress for point K. Okay, so let's take a look. For point K, the axial forces remains. Okay, but the torsion at K equal to TC. Okay, why is that? Because when I make the cut, if you review here, I have a TC going this way. So this is my K, and when I make a cut, I need to have the same moment or torsion to balance that. Okay, so the axial forces remains, but the torsion changes. Okay, so this is my axial plus torsion combined loading. Okay, now the question is asking, what about the principal stresses? All right, so for instance, I have basically for point H here, since I have the tau shear stress, and I have a sigma H, which is the axial stress, I can use the equation to find my principal stresses. All right, so basically I'm looking at a 2D element where I have a shear, tau H, and I have a compression, sigma H. Okay, so you can use Mohr circle to find the principal stress. Okay, use Mohr circle to find principal stress. Okay, all right, so you can follow the strategy and confirm the results as shown here. Okay, if you couldn't find a solution, please email me and I can chat you over the phone or through email. All right, okay, all right, so that is how we find stresses and torsion axial problem. Okay, and now let's talk about a steel shaft problem. Okay, this problem is actually quite similar to the previous problem, but the difference is that I have a little bit complicated issues in terms of external forces. Okay, So a steel shaft with outside diameter of 36 millimeters support 240 millimeter diameter pulley. Belt tension 2,400 Newton, 400 acting on the angle shown in this way. Determine the normal and shear stress on top surface of shaft at point H. B. Determine the principal stress and maximum in-plane shear stress. C. Determine the normal and shear stress on the side of shaft at point K. And D. Determine the principal stress maximum in-plane shear stress at point K. Show the orientation of these stresses in the appropriate sketch. Okay, so first thing first, I would like to see what type of forces I have on my system, All right, so observing this free body diagram on the wheel, okay, I need to figure out what type of forces I have on the wheel first. Okay, so this essentially give me the wheel. All right, and I have a force basically going like this by 2,400 Newton. Okay, force going like this by 400 Newton. First thing first is that I need to actually decompose. Let me use red here. Decompose these forces in terms of a horizontal and vertical. Is that right? And I will decompose in terms of a horizontal and vertical. Okay, so this drawing is inaccurate. Let me redraw it. Okay. All right. Okay. So if this is 15 degree, so this is 15 and this is 15 degrees. Okay. So let's call this F1 and let's call it F2. Okay. So further, I can decompose my wheels in terms of a F1 cosine 15 degrees. F1 sine 15 degrees. Okay. Correspondingly, I have F2. Okay. So this is basically 15 degrees also. So 15 degrees sine 15 degrees. F2 cosine 15 degrees. Okay. With all these forces, I combine them now on the wheel. Essentially, I have a force of a coupled moment, basically F1 cosine 15 degree multiplied by distance of this much, and F2 cosine 15 degree multiplied by distance of this much. Okay, and I know this distance right here is actually by the trigonometry. So this is 15. So this distance here is basically r cosine 15. And same here, r cosine 15. Okay, so the moment I will have equal to, if I set up the axis like this and make this to be positive, then my moment in terms of z-axis would equal to what? Would equal to a F1 cosine 15 degrees multiplied by r cosine 15 degrees minus F2 r cosine 15 degrees squared as well. Okay, so my moment equal to F1 minus F2 r cosine 15 degrees squared. Okay, so this is the moment I have. Okay, but be careful, this is only consider the horizontal forces. I also have the vertical forces going this way. Okay, so my moment has to add the horizontal component. Okay, so this is actually incomplete. Sorry about this. Okay, this is incomplete. So I have to consider the moment caused by F1 sine 50 degrees squared r minus F2 as well. So essentially my moment equal to F1 minus F2 r cosine 15 degrees plus a sine 15 degrees. Square. Okay. All right. So essentially, these are the bending moments I have. But you quickly realize that this is basically F1 minus F2 multiplied by R. All right. So actually, it took a long way to prove that if I want to find the moment on this wheel, you just need to sum the moments separately. Okay. Right? So mz equal to F1 minus F2 R. Okay. All right. Sorry I took a long way, but this is essentially proving that that is the moment caused by these forces. Okay. So this is all the forces I have. All the forces I have on this pulling wheel. Is that right? Not exactly. So what's missing here? So let me draw the figure again. So now I have a bending moment, which is mz. Okay, if I want to draw a double arrow, essentially I draw like this. Okay, and this is the cross section I'm trying to solve. Okay, don't forget, I do have a total force going this way. Okay, going this way. And that is equal to a combined forces. Combined forces. Actually, that combined forces here, so F here, would equal to a what? And by the way, if this is Y, let's set up our coordinate system accordingly. This is X, and this is Z. So this will be Fx equal to a minus F1. Then this is 15 degree. So of course, this is 15 degree. So F1 multiplied by a horizontal component of that. So what is the horizontal component of the F1? So this is 15 degrees. So F1 cosine 15 degrees, right? And minus F2 cosine 15 degrees. So basically Fx equal to a minus F1 plus F2 cosine 15 degrees. So that's all the forces, right? So this is the complete picture. Okay, and now here is the question. The question is asking you the stresses at H, stresses at K. All right, and you notice that H and K are both 160 millimeter away from the point of the wheel. So this basically distance is 160 millimeters. If I want to move this force to here, I will actually introduce another bending moment. And this bending moment is actually caused on the y direction. Okay, so this is my. So looking at this circular point here, looking at the circular point here, all I have is actually, if this is the cut, this is the tube, and my H is here, my K is here, this is my neutral axis, which also is my, this is my Y, this is my X, okay? I have a shear force going this way, which is Fx. I have a bending moment going this way, which equal to Fx multiplied by 160 millimeter. I'll also have a bending moment, right? Bending moment going this way, which is equal to F1 minus F2 multiplied by R. Okay, so my shear forces, right? So I don't have no axial force. Is that right? No axial force. My shear force equal to a Fx. Okay, my moment, I have 2 now, my equal to Fx multiplied by 160 millimeter, and mz equal to F1 minus F2 multiplied by R. Okay, now these are all the external forces I have. Okay, now after I find all these external forces, let's take a look at the cross-section here. Okay, see what kind of stress I will generate here. So on the top, I have H. Okay, so the shear force, Fx, don't forget is going this way, right? So the shear force will give you a shear stress at tau H. So tau H equal to Fx, and don't forget the Q, and this is the Q for it. Remember, and I, which is the moment inertia for the circular section, and B, in this case, is actually 2R. Okay, so Fx will give you the shear stress in terms of tau H. Right? How about the bending moment in the Z direction? So the bending moment in the Z direction is actually acting as a torsion. So tau H will also see a torsion component from Z, so that is mz multiplied by distance r and divided by j. Okay, how about the stress generated by y direction? Now this will be a normal stress for H, right? So the normal stress for H caused by this bending moment equal to moment multiplied by distance to the neutral axis. Now, the bending is actually going this way. So H is actually right on the neutral axis. So the distance is actually 0. So the bending stress is 0 for H. Okay. Now, for K, things are quite different. Okay, so Fx will give you a shear stress for tau K equal to Fx and Q over I 2R. Now this time, let me use a different color. It's basically this half. Right? Now, however, for the torsion, generate the shear stress tau K, I will basically have mz r over j again. Alright, because this will be the torsion. Okay, this will be the torsion. Okay, be careful though. This shear generated by F is actually going different way from the torsion. So not the same direction. Actually, if I want to say it, perpendicular. To each other. Is that right? They are perpendicular to each other. Okay, different shear stresses. All right. However, though, the bending stress for K will have values, and that is this. Okay, and it's actually in compression. Okay, so you realize that you cannot simply lump all the stress component. You have to judge based on the different locations. Okay, so with this thought process or strategy, I hope you can refer to the correct solution on the left and find your right answers. If not, call me or email me so we can discuss more. Okay? All right, so that is the problem. That is a problem for the torque, actually, for the wheel problem. I would like to review one more problem for you, and that is the post problem in subsequent videos.